Okay. Is the screen visible? Lecture 11.
Yes, sir.
Yes, sir.
Okay. So let's begin. Okay. So we are doing distribution fitting, and our main goal is ranking. Okay. When there are multiple options available, which is of course characteristic of NLP, be at the word level or phrase level or sentence level, everywhere we can have this ambiguity situation. Okay. And in case of ambiguity, we have to choose the correct option, and the choosing amounts to ranking and taking the option which is the highest rank. So this is a very characteristic business, very universal business in natural language processing. And to know the probabilistic ranking, we need to know the distribution, underlying distribution. If we don't know, then we'll take a non-parametric approach. We'll train a neural network with the data and hope that the neural network has learned the distribution. The shape is not known. We do not know whether it is gamma, beta, normal, binomial. I don't know what the distribution is. The neural network has observed the distribution, though the neural network cannot tell me what the distribution underlying is. Okay, if the neural network could speak, it could tell me that this is the distribution I have learned. And we also implicitly learn distributions all the time, even though we cannot articulate what the distribution is. Okay, so distribution is important for us, and we would like to fit a distribution to a piece of data if we guess that this would be the distribution. And after we fit the distribution, we have the instrument of chi-square probability, which gives us a way of measuring the accuracy of the distribution fitting subject to available information, subject to the data that is presented to us. Okay. So we have looked at how Poisson distribution can be fitted, multinomial or uniform can be fitted. And today we would like to take the other very famous distribution, probably the most famous of all distributions, which is called the normal distribution. So just by way of recap, we have to do distribution fitting, distribution learning, mainly because of scarcity of data. So when data is in short supply, we have to use transfer learning. And transfer learning is essentially borrowing the distribution of another domain or another data for the purpose at hand. So I think last time we remarked that suppose that you don't have data for movie domain, then we can use the distribution learned from book data for doing ranking in the movie domain data. And ranking is equivalent to decision making. I hope you understand that. Classification is a kind of decision making. And when we take up or when we select the class that has the highest probability, we are essentially doing ranking. So now transfer learning is essentially distribution adaptation, and distribution adaptation actually needs distribution fitting on the data. So I hope all of you are clear about the meaning of distribution fitting. In case some of you are new to the discussions, distribution fitting essentially means two things. One, assume that such and such is the distribution. Normal distribution is the underlying distribution. This is the first step. Second step is obtain the parameters of the distribution from the data. So distribution fitting is, first of all, deciding the distribution, and two, deciding the parameters of the distribution or computing them from the data. And the hypothesis that is tested or that is under scanner, the hypothesis that is under scanner is that the distribution D fits the data D, capital D fits the data small d. Now, this is our business. Now, let me also digress a bit here for 1 or 2 minutes and say that we have very definite methodology of computing the difference between two distributions. So if I have 10 numbers indicating a probability distribution, then these 10 values would be between 0 and 1, and their sum will be equal to 1. I have another 10 set of numbers, another set of 10 numbers, which are also between 0 and 1, and they sum to 1. That is also another distribution. So we can compute the distance between the two distribution by cross entropy, okay, by cross entropy measure, which many of you have already seen in the NLP class, machine learning class, and so on. Okay, so the distance between two distributions we can always compute by cross entropy. And the cross entropy loss is essentially measuring the distance between the learned distribution and the target distribution. Okay, if the numbers are between 0 and 1 summing to 1, then we are computing the loss as the distance between two distributions. So this is an aside. Now, transfer learning is actually reshaping the probability distribution. So now, maybe we remarked last time also that we have, let's say, data on dog. So in our case, the data is textual data. We have a corpus on dogs, and we want to make decisions based on the text. Now, for the word dog, I see the accompanying words distribution as bark, thief, friend, tail, carnivore, along with their probability values. The probability value are nothing but the proportion of frequency of these words in the whole corpus. So given a corpus, let's say on the topic of dog, this is the domain, I can find out the frequency of words co-occurring with the word dog. Okay, so bark is likely to be a very frequently co-occurring word. So here I say that probability to be 0.14. Similarly, for cat, I see that the probability of mu is also 0.14. Okay, and the distribution of the words which are in the vicinity of cat look similar to the distribution of the words which are in the vicinity of dog. So cat and dog have distribution similarity which are indeed in turn similar. Okay, so the contextual words of cat and dog are similar. Their distributions are similar. On the other hand, if I take the word lamp, the accompanying words can be candle, light, flash, stand, shade, watt, home, bulb. These are words closely related to lamp. So first of all, they do not intersect with the set of words in the vicinity of cat or dog. And also their distribution shape, that means this shape of bars, is different from that of cat or dog. So now the interesting consequence of this is that if I have no corpora related to cat, okay, I can still make use of the machine learning model which has been trained on dog corpus and do NLP. Okay, so I can do NLP on cat text based on dog text. Okay, so if I ask the question, for example, how many legs do cats have? Okay, and I have not seen any text corresponding to cat. How many legs do cats have? Then the word leg will trigger the number 4. Okay, the word leg will trigger the number 4. I'm repeating this for the machine learning model trained on dog corpus, and our answer will come out to be 4, which happens to be correct in this case. Okay, do cats like milk? Dogs also like milk. Okay, so the answer will again come out to be yes. If I want to translate, for example, cat sentences, do machine translation on cat sentences. Okay, this cat is large. or this animal is large. I find this sentence in the cat corpus and I am required to translate. I can make use of the machine translation model trained on dog corpus. Okay, and if the translation is from English to Hindi, I'll be able to produce some translation of the cat sentences based on the machine translation model trained on dog corpus. Okay, but I don't think I'll be able to do this very effectively for a machine learning model trained on lamb corpus. Okay, so there is a notion of domain similarity. Cat and dog domains are similar to each other, more similar than cat and lamb. Okay, so and this domain similarity is really measured from the probability distribution of words and phrases and n-grams composing that domain. So I collect the n-grams starting from n equal to 1 going up to, let's say, 4, 5 in the dog domain and look at their probability distribution. So these probabilities of these n-grams are extremely useful building blocks for me for creating NLP systems. Okay, and this computation of parameters need not be frequency based. I can train a neural language model, as you have seen in deep learning for NLP course. I can train a neural language model, and that neural language model trained on dog corpus will serve well for cat corpus also. Okay, so this is the strength of working with probability distributions. If our decisions were completely 0, 1, black and white, we would not have that flexibility. Okay, and neural language model brings in more flexibility by allowing us to operate in a continuous domain. Okay, so if the domain is continuous or the space is continuous, then extrapolation, interpolation, they work well because the gradient is existing from point to point. Okay, so so this kind of observation is important for us to see that distribution plays a very important role. Proceeding further, we have also seen that in NLP, ML, speech, computer vision, AI, whole of AI, we are frequently required to compare our figures with baselines. And in the baseline comparison, we really have to see the distance between baseline distribution and our obtained distribution. This again takes us to computing the distance between two distributions. So everything is centered on distribution, and distribution plays such an important role in all this. Now, fitting distribution to the data is what we have been discussing so far. And just by way of recap, you will remember that we tried to fit Poisson distribution through proverb data. And Poisson distribution was invoked because that distribution has the property of being able to tackle rare phenomena. Okay, so Poisson distribution fits the distribution of rare phenomena. And we took one NLP situation where the phenomenon was indeed rare. This was the appearance of proverbs. Okay, so we have some data of 50 documents. Okay, any data that we can lay our hand on is very valuable because it removes some uncertainty. So here we have 50 documents, and we find that 21 documents have no proverbs, 0 proverbs. 18 have 1, 7 have 2, 3 have 3, and 1 has 4 proverbs. So that actually also is consistent with the fact that proverbs are rare occurrences. You do not have many proverbs occurring in a single document. So we thought that, yeah, since proverb is a rare phenomenon, Poisson distribution will be a good guess at the underlying distribution. And again, reminding you that if I know the distribution and if I know the parameters of the distribution, I do not have to go through a complicated procedure of training based on the data. I don't have to run a neural network training algorithm. on huge amount of data. So, so this point is important, the point that I'm making. If I know the underlying rules, I don't have to learn. Okay. If I know the underlying distribution, again, I don't have to learn or train on the data. But rules can be produced from my knowledge of the problem, from my understanding of theory. Distribution requires some data to be given. Okay. And also appreciate the fact that making a correct guess at what the underlying distribution is a tremendous step. Okay. It depends on, again, our knowledge of the problem. So just reflect for some time on the proverb problem again. So the fact that proverbs are rare is a language phenomenon. We look at the corpus, we understand the property of the language, and understand that proverbs are rare. Now, what is the meaning of proverbs? I am operating with a specialized knowledge in this case. I understand what is the meaning of proverb. The machine doesn't. The meaning of proverb. Okay, as a human being, I know the meaning of proverb. Somebody verify that I am audible and you're looking at the proverb slide.
Yes, sir. You're audible.
Yes, I'm audible. Yeah, and you're looking at the proverb slide. Yeah. So I'm bringing in knowledge which the computer doesn't have. What is the meaning of proverb? Okay, a proverb is a sequence of words, a fairly fixed expression. Again, I have knowledge of something called fixed expression. That is expressions whose constituents cannot be changed and which have a particular meaning in combination. Okay, Nach na jane angan tera has a particular meaning. It is referring to the incompetence of a worker. It is not referring to dancer, dance, and even angan. The intended meaning is the incompetence of a worker. So, so in Sanskrit, there has been a lot of work on meanings of expressions, and there are three kinds of meaning: Avidha, Lakshana, Vyanjana. Avidha, Lakshana, Vyanjana. We would like to talk about it at some point of time. So, how a sequence of words or how a language expression refers to an entity by way of meaning, okay, in what manner, that manner decides, is it Avidha or Lakshana or Vyanjana. Okay, so proverbs have high degree of Vyanjana. Okay, they refer to something which are not exactly contained in the meanings of the constituent words. Proverbs are typically uncompositional. So I have the meaning of proverbs in my mind. They point to some eternal truth, okay, by making use of commonplace day-to-day expressions, day-to-day occurrences of words. Nach na jane angan tera, a bad rider quarrels with the camel. So this is proverbs. So I have a understanding of proverb. And I also know that proverbs occur rarely. This is another tremendous piece of knowledge. Computer doesn't know this. Okay, so I know what is a proverb. I know that proverb occurs rarely. These are very critical pieces of knowledge. And making use of this knowledge, I say that most likely the underlying distribution is poison. So this is a very big leap. Okay, even though we are not aware that we are making tremendous steps in inferencing, and these things are very intelligent. So the knowledge of proverb, where is it contained, by the way? It is in my brain, and there is attempt at capturing this kind of knowledge outside the machine learning model through what is called the knowledge graph. Okay, so those of you who are aware of knowledge graphs and are working on knowledge graph would appreciate this point, that as human beings, we carry many knowledge graphs, very rich knowledge graphs, and very large knowledge graphs in our brain all the time when we make decisions and do inferencing and do any kind of synthesis, natural language generation, drawing a picture, we carry knowledge graph. The computer doesn't have the knowledge graph per se. It has to be endowed with knowledge graph and has to be integrated with the machine learning model for effective operation. Okay, so I decided that Poisson distribution is probably a good fit. It is unlikely that the computer will be able to do this by its own, on its own. So now there is a mechanical procedure. Okay, I have these numbers in front of me. This is my data. Then you will recall that assuming that this is Poisson distribution, I am required to find out what this lambda is. This is the parameter of the Poisson distribution. So the probability that the random variable capital X takes a value small x is given by e to the power minus lambda to the power x by x factorial. So now how do I get lambda? I get lambda by maximum likelihood estimate principle from the data itself. Okay, from the data itself. And here, what is the specialized knowledge I'm using? The specialized knowledge is this, that this parameter lambda happens to be the mean of the Poisson distribution and also its standard deviation. This is a property of Poisson distribution. And statistician, probability theorist has given me this convenience that I can find out lambda, which is the defining parameter for Poisson distribution, through the medium of mean finding. And another thing I am making use of is that mean finding is best done by maximum likelihood estimate. I take the values and I find that the mean is 0 into 21, that is value into frequency, 1 into 18, 2 into 7, and so on. This is 45 by 50, which is 0.9. So 0.9 is the mean of the estimated mean of the Poisson distribution, and that mean is lambda. So I am done with getting this probability expression, Px equal to x e to the power minus lambda to the power x. Okay, and now I'm absolutely fine. Now I would like you to document in your mind the kinds of knowledge that we have made use of. First, I have made use of the knowledge of what is a proverb. I have made use of the knowledge that proverb is a rare phenomenon. Third piece. Fourth piece, I made use of the knowledge that the parameter of Poisson distribution is actually the mean of the Poisson distribution. Okay, that is another piece of knowledge. Fifth piece of knowledge is that the mean, as evidenced in the data, is the mean of the underlying distribution. You cannot do anything better. This is maximum likelihood estimate principle, that the best estimate of population mean is the sample mean. So 5 pieces of knowledge, critical pieces of knowledge, they are in my brain, in my own neural network. Okay, and these 5 pieces of knowledge have been crucially used, without which I cannot make progress. So, so there are things beyond deep learning, beyond machine learning, without which machine learning will fall flat on its face. Okay, so always be aware when you're doing machine learning as to what are the other pieces of knowledge which are being brought to play in the current situation. What are the other hidden pieces of knowledge, allied pieces of knowledge, related piece of knowledge, which are brought to play. Be aware of that. And even I can also still go further and say that even computing the mean, okay, the definition of mean and the computation of mean this way, this is nothing but the weighted mean. How this is another piece of knowledge which I'm making use of. Okay, and if you allow me, everything that I'm doing, drawing a table here, putting 2 columns, all these are tremendously intelligent activities. Okay, and they are brought to play when we are training a machine on data and doing AI. So now I can calculate the expected number of proverbs given the given that I have obtained lambda. So probability of x equal to 0. The probability given a document, the probability that it contains 0 proverb, that probability is 0.4. Okay, contains one proverb, 0.37, 2, 0.17, 3, 0.05, 4, 0.01. So the methodology is clear. I assume the probability distribution, get the parameter from the data, and then get the probability values of the random variable taking a particular value. So from the probability value, now I can get the expected number of documents containing 0, 1, 2, 3, and 4 proverbs. So probability of getting 0 proverbs in a document is 0.4. There are 50 documents. So 0.4 into 50 is 20. The probability of getting 1 proverb in a document is 0.37. There are 50 documents. 0.37 into 50 is rounded off to 80. And similarly for 2, 3, and 4, I'll get the expected values of the expected value for the number of documents. Now I do a visual inspection. The actual observations are 21, 18, 7, 3, and 1. These 5 numbers. Expected numbers are 20, 18, 8, 2, and 1. Looks like the numbers are not very different from each other. This array of 5 numbers on the observed front and array of 5 numbers on the expected front, they do not seem to be very different from each other. Okay, but I have a more systematic way of saying that the expected numbers are not very far from the observed numbers by means of the instrument of chi-square distribution. So what I do is that I find out the difference between observed and expected, raise it to the power 2 divided by expectation, and this I compute for each category. 0, 1, 2, 3, 4 are the number of proverbs. So there are 5 categories. So for each category, I have the quantity observed minus expected square by expected, which are 0.05, 0, 0.125, 0.5, and 0. I sum all this up, and this I call the observed chi-square. Okay, this is my observed chi-square. We are coming to the theory very, very quickly, very soon. And then chi-square observed is for this problem is turning out to 0.675. Now, since there are 5 categories, the degree of freedom is 4. And I want to be 95% confident that the distribution is, underlying distribution is indeed Poisson. Or my probability of error should be less than or equal to 0.05. Okay, alpha value, significance value is 0.05. So consulting the chi-square table, I find that chi-square critical is 9.48. Now chi-square observed is less than chi-square critical. So this means that the chi-square observed, okay, to the right of chi-square observed, there is a higher level of probability. There is a bigger area compared to chi-square critical. So chi-square observed, okay, covers more probability area than the chi-square critical. So in such a case, we have no ground for rejecting the null hypothesis. The null hypothesis was that the data follows the Poisson distribution. So this part is a bit mechanical, but we are today making a bit of progress towards why this mechanical procedure works, okay, why this technique works. So let's remember for now that if chi-square observed is less than chi-square critical, then we cannot reject the null hypothesis. I'll repeat this very important statement. If chi-square observed is less than chi-square critical, the null hypothesis cannot be rejected. Okay, you cannot say that I'm accepting, though for practical purposes you will do so. It is more correct for you to say that based on the available information, I cannot reject the null hypothesis. The null hypothesis in this case is Poisson distribution. So this is a fairly mechanical procedure, and alpha chi-square critical is essentially a vertical line drawn at this point such that the area from this point to plus infinity is 0.05. The significance level is 0.05. The next problem that we saw last time. Okay, so Pranjali is saying, suppose we assume that the data follows normal distribution and proceed in the same manner. So if the distribution is not right, you will find that chi-square critical, chi-square observed will not be less than chi-square critical. Okay, that's where this will fail. Okay, normal distribution is coming. Just wait a bit. So fitting a normal, should be called my multinomial distribution. And a special case of multinomial distribution is uniform distribution. So throwing a dice. Now we saw last time that we are tossing a dice 120 times, and we are testing the hypothesis that the dice is fair. If the dice was fair, the frequency of each phase would be 20. Frequency of appearance of each phase will be 20 in the most ideal condition. So since they are not 20, can we outright reject the hypothesis that the dice is fair? No. So last time we discussed that the phase that appears when we throw the dice is a function of my position of the hand, okay, maybe my body temperature, the wind condition around, the amount of noise present in the vicinity, many imponderable parameters, unknowable parameters that influence this this phenomenon, that is the phase that appears. So I cannot accept the hypothesis without a proper procedure, nor can I reject the hypothesis just based on the data, because there are many other influencing factors. However, if the dice was fair, then there would be uniform distribution underlying, and the probability of appearance of each phase will be 1/6. Now the procedure is very mechanical, as you know. You multiply the probability by the number of experiments. So number of experiments here is 120. Dice has been thrown 120 times. So 120 into probability of appearance of 1, 2, 3, 4, 5, 6 will give me 20. Okay, because the probabilities are uniform distribution. So this data of 620s, do they agree with these observations? 25, 17, 15, 23, 24, 16. Do they agree? Agree means what? We have to apply the same procedure. So I do again observed minus expected, and observed minus expected square divided by expected, and take this quantity for each category. There are 6 categories, sum them up. When I sum them up, I get 5, and 5 is chi-square observed. Now I would like to know what is the value of chi-square critical. The degree of freedom is 5, 6 minus 1, 5. Significance level is 0.05. And consulting the chi-square table, I find that chi-square critical is 11.07. Now the chi-square observed is less than chi-square critical. 5 is less than 11. So I have no basis of rejecting the null hypothesis. The null hypothesis was that the distribution underlying is uniform, or the dice is fair, which is equivalent to saying that the dice is fair. All right. So so this is again the same procedure like Poisson, which is telling me that I cannot reject the hypothesis that the dice is fair. Finally, I come to fitting the normal distribution. We all know that the most famous distribution is normal, bell-shaped curve, and many interesting quantities in real life follow normal distribution. Okay, so let's see how to fit the normal distribution. There are a few subtleties involved here. Okay, some small tricks and some small adjustments are needed. So this is the cricket score problem, where I am studying the performance of a batsman. Maybe as a selector, I am interested in knowing should I select this batsman or not. Okay, so how do I work? I work with data, right? Decision making is a function of data. So I have collected these data, that this batsman has scored in the range of 0 to 20 10 times, 21 to 40 30 times, 41 to 60 50 times. Oh, no, I'm sorry. Scored in the range of 0 to 20 10 times, in the range of 21 to 40 20 times, In the range of 41 to 60, 40 times. 61 to 80, 80 times. 81 to 100, 10 times. So this is really a well-shaped behavior. Okay, not very low scores, not very high scores. A kind of the tendency is to cluster around the score from 41 to 60. So these ranges are plotted so that the data is not very long to present. Actually, there are 100 innings, and for each innings you have the cricket score. And ideally, you would like to apply all this procedure on each data point, that is 100 data points, which is easy programmatically. But I've taken a more succinct representation of the data in terms of range. So 0 to 20, I take the midpoint as 10, 21 to 40, 30, 41 to 60, 50, 61 to 80, 70, 81 to 100, 90. So these midpoints are representatives of the range. That's what I have assumed. And this range appears 10 times, 21 to 40, 20 times, 41 to 60, 40, 61 to 80, 20, 81 to 100, 10. Okay, this is how the frequency is. So now we apply the standard procedure. I want to know the mean and standard deviation of the normal distribution. Okay, because the normal distribution is defined by these two parameters. How do I do it? I compute the mean from the data. Okay, now the midpoint 10 into frequency 10, 10 into 10 is 100. Midpoint 30 into number of times is 20, so 30 into 20, 600. 50 into 40, 2000, 70 into 20, 1400, 90 into 10, 900. So total number of innings is 100 and total weighted sum is 5000. So the mean is 50. And 50 is the best estimate subject to available information for the underlying distribution's mean. You cannot do better. Okay, so this is a proof that we need to do at some point of time, that maximum likelihood estimate gives you the best estimate of the underlying parameter. So for the normal distribution, then the best estimate of the mean is 50. We need to compute the standard deviation also for the normal distribution. See the methodology. So the midpoints are 10, 30, 50, 70, 90. Number of times they appear is 10, 20, 40, 20, 10. So I have to take midpoint into frequency, so 100, 60, etc., etc., which was done like before. 100, 600, 2000, 1400, and 900. Now I take the value minus the mean. So 10 is the value, minus the mean is 50. 10 minus 50 is minus 40. 20 minus 50, 30. 10 minus 50 is minus 40. 30 minus 50 is minus 20. 50 minus 50 is 0. 70 minus 50 is 20. 90 minus 50 is 40. Now the procedure of standard deviation computation one requires me to square this difference. I square this difference and get the sum as 4000, but that's not important. So square of the difference to the power 2 has to be multiplied by the frequency. Now frequency is 10. 10 into 1600 is 16,000. 20 into 400 is 8,000. 40 into 0 is 0. 20 into 400 is 8,000. 10 into 1600 is 16,000. So I sum the frequency into square difference between mean and value, and summation gives me 4,800. Okay, so this 48,000. So 48,000 divided by 99. Okay, why it is not divided by 100 but 99? There is a small theoretical point about standard deviation. So 48,000 divided by 99. What is 99? 100 innings minus 1. Gives me variance as 484.848. standard deviation is 22.01. I can take this as 22. Okay. So standard deviation also I have computed. Where did I compute from? I computed it from the data. So the best estimate of standard deviation and best estimate of mean for the population is this. You cannot do anything better than that, given the information. So now I have got both the parameters. It will now be easy for me to compute the probabilities in this range. So probabilities in this range into 100 will give me the expected frequency. Observed frequency I have already got. So that part is little involved. It involves properties of normal distribution. One thing I have to do, otherwise my calculations will go wrong, is that normal distribution is a continuous distribution, but the ranges are all discrete, 0 to 20, then there is a gap, and then 21 to 40. It is okay because the cricket scores are actually integers. So you cannot have 2.5 as the score in an innings. So since that is the case, then this working with ranges is fine. But when I say that I would like to fit normal distribution to this data, I have to be careful. Okay, I have to make these ranges flow smoothly into one another. 0 to 20 range will have to smoothly transit to 21 to 40. 21 to 40 will smoothly transit to 41 to 60. This smooth transition is ensured by introducing the value 0.5. So 0 is looked upon as minus 0.5. 20 is looked upon as 20.5. So this range 0 to 20 is converted to a continuous range from minus 0.5 to 20.5. Surely, practically speaking, no batsman can score minus 0.5. No, not possible. But it is for the purpose of mathematical accuracy. So 21 to 40 is converted to 20.5 into 40.5. 41 to 60, 40.5 to 60.5. 61 to 80, 60.5, 80.5, 81 to 100, 80.5, 100.5. So low and high of continuous ranges are obtained this way, as you can see on the screen. Please somebody verify you are seeing continuous values on the screen.
Yes, sir.
Yes, sir. Yes, sir.
So now what I do is that I have to now I have to proceed towards standardizing the normal variables, because in that case I'll be able to use the z-score values, and for that it is necessary that I subtract mean from the random variable values. So minus 0.5 minus 50, 50 is the mean, so minus 50.5. 20.5 minus 50 will give me minus 29.5. 20.5 minus 50 minus 29.5, 40.5 minus 50 minus 9.5. So this way, each range is now converted to x minus mu values. So minus 50.5 minus 29.5 minus 29.5 minus 9.5 minus 9.5, 40, 10.5, and so on. Okay, so the discrete ranges 0 to 20, 21 to 40, etc. have been converted into continuous ranges subtracted by mean. Now to standardize a variable into the standard normal variable form, we have to divide it by standard deviation. So standard deviation was 20. So we proceed and we find that Z low is minus 2.3. This is okay because you see, yeah. So X low when subtracted by mean was minus 50.5. When you divide it by standard deviation 22, you get minus 2.29. Okay. So Z low is minus 2.29, Z high is minus 1.34. How? Because minus 29.5 divided by 22 is minus 1.34. So this way, or from all the 5 ranges, I get Z low and Z high values. Okay. And Z low and Z high values are required for me to get the probability within the range. So proceeding this way, I have Z low and Z high in the 5 categories. So Z score value from my from the Z score table are the values obtained from the Z score table. So Z score low, okay, the Z value was minus 2.29. Z score, okay, which is obtained from the table, is really the area from minus infinity to minus 2.29. Minus infinity. So that probability is 0.011. And Z high is also minus infinity to that particular Z high value. So Z high value was minus 1.33. So I get the value as 0.09. So subtracting Z score low from Z score high, I get the range probability. So you see the range probabilities are coming out to be 0.0791, 0.2435, 0.35, 0.23, 0.07. So this is the probability of the batsman scoring in that range 0 to 20. That probability is 0.08 if the values come from a normal distribution. Okay, so you see this was little more involved compared to Poisson or uniform distribution. Here we have to make use of the Z score table. For that we have to subtract the mean divided by standard deviation. Okay, so that is the little more involved part. So all range probabilities are known, frequency is known, there are 100 innings. So then I get the expected frequency as 7.91, 24.35, 35.08, 23.33, 9.33. All these are expected frequencies, 100 into range probability. And they sum to 100. Of course, the discrete values also sum to 100. Now, this is the expected frequency. And the observed frequency we need to see. Observed frequency is 10, 20, 40, 20, 10. Expected frequency is 7.91, 24.35, 35.08, 23.33, 9.33. Okay, sometimes the expected value is more, sometimes it is less than the observed value. Therefore, now by inspection, we cannot say anything. We need the instrument of chi-square probability. So, but looking at the data, on the first impression, what do you think? You probably think that, yeah, may not be so far after all. The normal distribution may not be such a bad guess, maybe. Because you see 10 and 8, 20, 24, 40, 35, 20, 23, 10, 9, not bad. Okay, they're close. So let's apply chi-square distribution theory. So I get observed minus expected, then observed minus expected square and divided by expected. Do it for 5 categories. So chi-square observed is coming out to be 2.54. What about chi-square critical? Chi-square critical is coming out to be 9.48. So there are 5 categories. So degree of freedom is 4. Alpha value is 0.05. Chi-square critical, by consulting the chi-square table, it is 9.48. So since again chi-square observed is less than chi-square critical, I cannot reject the null hypothesis. The null hypothesis was the data is coming from normal distribution. Okay. So whatever we have done so far, why is null hypothesis stated the way my procedure, all my computation and calculation were based on the distribution that I have assumed. Okay, so the distribution that I have assumed is forming the null hypothesis. Okay, so remember that whenever we fit distribution fitting, the assumed distribution forms the null hypothesis. And because the null hypothesis is established, I can proceed further. Otherwise, how do I proceed? If I do not assume that normal distribution is the distribution, I cannot really make those steps of calculating the mean, the standard deviation. What is the basis of calculating mean and standard deviation? Why? Well, because I have assumed normal distribution, I am taking all these steps starting from that hypothesis. And then I'll go back and verify the hypothesis based on the chi-square distribution. So this, by now, I think through these 3 examples, you have become quite familiar with how chi-square distribution works, okay? How hypothesis testing happens based on chi-square statistics. So, but now the natural question then arises is why chi-square? So we'll do this in more detail in the next probability lecture. I'll just give you a feel for the proof, why chi-square. So you see, we are dealing with a random variable t, which is observed minus expected square divided by expected, summed over all categories. And then we made use of chi-square table. So where is the proof that this t, this quantity t, observed minus expected square by e, summed over all categories, follows chi-square distribution? Okay, who told us that this follows a chi-square distribution? Well, the proof is somewhat involved, but we'll first check it for two categories. Okay, now if it is two categories, then there are two random variables, x1 and x2. x1 plus x2 is equal to n, and let the probabilities be p1 and p2. p1 plus p2 is 1. So observed minus expected is x1 minus np1 square divided by np1, observed minus expected square by expected. Similarly, x2 minus np2 square by np2. Now I do this algebra. I replace x2 by n minus x1, p2 by 1 minus p1. And after doing these mathematical steps, I come to a expression. This is x1 minus np1 square by np1 into 1 minus np1. Okay, so t is equal to x1 minus np1 square by np1 into 1 minus np1. What do I conclude from there? RHS is an expression where the mean of binomial distribution is being subtracted from the random variable, and the subtracted quantity is divided by the standard deviation. For binomial distribution, the mean is np1 and the standard deviation is np1 into 1 minus p1. Okay, so then the whole thing is raised to the power of 2. Now we know that binomial distribution, in the limit as n increases, binomial distribution approaches normal distribution. Okay, so this RHS is indeed a normal distribution of single random variable. So there were two random variables, and we have on the right hand side one single normal variable. So this is 2 minus 1, the degree of freedom. Okay, and this is the square of a standard normal variable, which is by definition chi-square distribution. Proof is not complete. Okay, it is only a hint of what is coming. Okay, for two cases, this kind of algebra works. For n cases, we'll have to do integration over volume. Integration over volume, and then that will establish the proof. Okay, so let me stop today and see if there are any questions. Any question? Okay. Okay. So looks like there is no question at this moment, or is it there? Prince.
Hello. Yes. So I just wanted to ask, for transfer learning, is it always necessary that the two distribution needs to be similar?
Yes, the common answer is yes, right? The reason is that the distributions of n-grams are similar. Okay, and these distributions of n-grams, which are essentially the n-gram probabilities or the language models, they are the building blocks of downstream NLP tasks. Okay, so that is the reason. But if you want a more rigorous mathematical proof in what form? That if the source distribution is within epsilon distance from the target distribution, then the error will be a delta. Okay, a delta where so see this mathematical statement. let the distance between the two probability distributions be epsilon, and let the error be delta. Then as epsilon tends to 0, delta also will tend to 0. Okay, so that is the rigorous mathematical statement of what is transfer learning. Okay.
Sure, sir.
So this delta cannot approach 0 as epsilon tends. Sorry. Okay, let me take the contrapositive. So delta cannot. For delta to be 0, the epsilon has to be 0. Epsilon also has to tend to 0, which means that the two domains distributions have to be similar. Okay. Yeah. So we'll now close this discussion and then meet on a different link, Gmeet link, which Kaveri has sent for information extraction work update. Okay, thank you.
Yes.
Thank you, sir.
Thank you, sir.
Yes, sir. Thank you, sir.